Okay, this is the second batch, Friday, 26th day of June 2026. Still discussing CHEM102. We are now in the second batch. If you're not yet part of this program, I don't know what you are waiting for. Now, we'll be talking about the man we call amphoteric nature of Alkanols. Amphoteric. Look at the word. Amphoteric. Amphoteric nature of alkanols. The man of the moment is alkanols. We are still on alkanols. And we are discussing their amphoteric nature. You know, when you talk about amphoteric, it means the ability to behave as an acid as well as a base. So anytime somebody tells you that something is amphoteric, it means that that thing behaves as an acid as well as what? A base. Okay. Remember that if you look at somebody like water, UNN will bother you with that. If you look at water, that is H2O, the man you call water. This water can function as an acid. The same water you know can function as a base. In fact, the language we use is that water is amphiprotic. Water is amphiprotic. It means that water can serve as a proton donor as well as a proton acceptor. That is what it means to be amphiprotic. And of course, you know that any chemical species that is capable of donating proton, a proton donor, is known as Bronsted-Lowry's acid. Proton donor. Any chemical species that is capable of donating proton is an acid. And any chemical species that is capable of accepting proton acceptor, is a base. So if water can donate proton, it means it can function as Bronsted-Lowry's acid. If the same water can accept proton, it means it can function as Bronsted-Lowry's base. In that case, water can be amphoteric. It can behave as an acid as well as a base. Why? Because it is amphiprotic. We're going to relate that to what is happening in alkanols. Let us even, show you what we mean by this. I guess you know that when we talk about proton, in this course, proton can be seen as hydrogen ion. Take note of that. Hydrogen ion is seen in this course, CHEM102, as a proton. I hope you know that inside hydrogen ion, there's no electron there. Are you aware of that? No electron. Reason, the normal hydrogen you know, mass number is 1, atomic number is 1. Okay? The number of neutrons is A minus Z, which is 1 minus 1. That gives you 0. There's no neutron there. Are you with me? Now, if the same hydrogen, which has only 1 electron, the atomic number is 1. Remember that proton number is equal to electron number, which is equal to atomic number. For a neutral atom, the atomic number Z is equal to number of electrons, which is also equal to number of protons. Are you with me? So when hydrogen that has only 1 electron loses that 1 electron, it becomes hydrogen ion. So what it means is that in hydrogen ion, the only electron the atom has already been lost to form this. So this person is seen as a proton in this course. Take note of that. Alright, we are moving to somewhere. Just trying to give you the right background so you can follow what we are doing. Now, if I react HCl with water, class, let's see what we are going to produce. HCl is reacting with water. What happens? You're going to produce hydrozonium ion plus chloride ion. Take a look. HCl is reacting with H2O. What did I produce? H3O plus hydrozonium ion plus chloride ion. What do you think has happened? This person has donated his proton to water. Here is H2. There are 2 atoms of hydrogen. But here, what do I have now? H3. That means that this HCl has donated its proton to water. This is hydrochloric acid. As an acid, it's a proton donor. It has donated its proton to water to become hydrozonium ion, leaving it with just chloride ion. So in this reaction, water is a proton acceptor. Water is who? A proton acceptor. And anybody that accepts proton is a base. So water here is functioning as a base. Reason, it can accept a proton. So it's a proton acceptor. I hope you're here. Okay. Let us also take a look at somebody when the same water reacts with ammonia. This is ammonia plus water. Let's see what happens. Now, I'm going to produce ammonium ion plus hydroxyl ion. What has happened? Follow me. You notice that here I have 3 atoms of hydrogen. But in the product ammonium ion, I have 4 atoms of hydrogen. So what do you think has happened? The water has donated its proton to ammonia. The water has donated its proton to ammonia to convert it to ammonium ion, leaving the water with just hydroxyl ion. So in this case now, you see that water is a proton donor. When it reacted with HCl, it accepted hydrogen from HCl, hydrochloric acid, to become hydrozonium ion. So it's a proton recipient in that case. But here, the same water is now donating proton to ammonia to form ammonium ion. So any proton donor, according to Bronsted-Lowry, is an acid. So water here is behaving as an acid. So you see that water has the ability to donate proton. It also has the ability to accept a proton. That's why we say that water is amphiprotic. Amphi. You know, in sciences, anytime you hear amphi, means dual nature, dual. That's why when you say amphibians, organisms that live in water and also on land. That's amphi. So amphoteric, it means the ability to function as an acid as well as a base. So when you say amphiprotic, it means the ability to donate proton as well as accept what? Proton. So that is water. Now let's come back to the onus of the matter where UNN, UNIZIK, and all those universities will bother us with. Follow me. There's no examiner in CHEM102 that will not ask you question on what I'm explaining here now. Follow me, oh, follow me. Class, you notice that in this course, CHEM102, there's what we call organic acid. Which class of organic compounds represent organic acids? They are carboxylic acids. Carboxylic acids. This is the class of organic compounds we call organic acids. Their general formula is RCOOH. So the functional group, this COOH you have here, is the functional group, which we call carboxyl. Carboxyl functional group. So anybody that has the COOH group, the carboxyl group, is a carboxylic acid. So they represent the class of organic compounds we call organic acids. So if they ask you to give the example of organic acids, begin to mention members of carboxylic acid. Okay? Ethanoic acid, propanoic acid, butanoic acid. They stand as the class of organic compounds we call organic acids. Okay, I've talked about organic acids. So now, who are the people you call organic bases? Organic bases. Organic bases. So the ones you call organic bases, they are the amines. Amines. Their own general formula is R. Of course, you know that R is an alkyl group, which is alkane that has lost 1 hydrogen atom. When a member of alkane loses 1 hydrogen atom, it becomes an alkyl group. Now, if that alkyl group is bearing amino group, the amine group, NH2, what you have produced is called an amine. This is the general formula for amines. So if I write something like this, CH3, which is methyl group, an alkyl group, then I add to it NH2, I have produced an amine because it obeys the formula RNH2. So I'm going to name this as methylamine. Methylamine. So amines or amines, as the case may be, they constitute what we call organic bases. Take note. When they say which of the following is an organic base, begin to look for an amine with the general formula RNH2, where R is an alkyl group. Okay. I've talked about organic acid. I've talked about organic base. I hope somebody follows. Next will be organic salts. Who are the people you call organic salts? Very paramount. The class of organic compounds you call organic salts are the esters. 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 Their own general formula they obey is RCOOR. RCOOR. Two alkyl groups. They can be the same or different. That's why I put prime in one of them. Okay? Two alkyl groups separated by the COO group gives you an ester. Example, CH3, COO, C2H5. Take a look at this. This is an alkyl group, which is methane. Methane is CH4. When it loses one hydrogen atom, it becomes CH3. That's alkyl group. Ethane, second member of alkanes, is C2H6. If it loses one hydrogen atom, it becomes C2H5. So this is an alkyl group. So when you have two alkyl groups separated by the COO group, that gives you an ester with general formula RCOOR. Are you with me? Now, if you want to name this ester now, first of all, you name the alkyl group that ends it. So you say ethyl, because this is an ethyl group. You count the remaining number of carbon atoms, 1, 2. So you say ethanoate. Ethanoate. Another name for esters is alkanols. That's why their names end with noate. Does that make sense? But that's by the way, we are coming to all these things. But the news is that the class of organic compounds we call organic salts. They are which people? Esters. Who are the organic acids? Carboxylic acids. General formula RCOOH. Who are organic bases? Amines. General formula RNH2. Who are organic salts? Esters. General formula RCOOR. Finally, there is somebody which is the man of the moment. There is a particular person that behaves as an acid as well as a base. That one is alkanol. An alkanol functions as an acid as well as a base. In what class? Take a look. That's why UNN will ask you something. They will write a chemical reaction and ask you, this particular alkanol here, is it functioning as an acid, as a base, as a salt? Are you with me? They will ask you. So when you see any chemical reaction involving an alkanol, you should know what the function the alkanol is playing in that chemical reaction, whether it's behaving as an acid as well as a base. How do you know? By understanding the mechanism of the reaction. Just follow me. Follow me. Let's take a look at somebody like, let's say we have methanol. Let me take methanol. Methanol is, this is methanol. I need to draw this out for clarity purpose and avoidance of doubt. That's methanol. An example of alkanol. What is the functional group? OH group, hydroxy group. The reactivity of an alkanol is as a result of the hydroxy group. Alkanol behaves the way it behaves because of the presence of the hydroxy group, which is the functional group. Okay? So the chemistry of an alkanol is a function of its functional group, which is the hydroxy group. Now, in chemical reaction involving an alkanol, it can involve the breaking of oxygen-hydrogen bond. This bond here can break. Did you hear what I said? Chemical reaction involving an alkanol. I'm talking about the mechanism now. What happens? The mechanism means step-by-step series of events that convert reactants to products. That's the mechanism of the reaction. Okay? Now, a chemical reaction that involves alkanol with hydroxy functional group, OH is bonded to carbon, can involve the breaking of oxygen-hydrogen bond. This bond here will break. When that happens, hydrogen will be given out. Now, reaction of alkanol can also involve the breakage of carbon-oxygen bond. Carbon-oxygen bond. It is either oxygen-hydrogen bond. Please take note of this. This is where they will bother you with. That's the technical part of the course. When alkanol wants to react, it's either that oxygen-hydrogen bond is breaking or carbon-oxygen bond is breaking. And that will tell you what the alkanol is behaving like, whether as an acid or as who somebody, a base. My people, if the reaction involving an alkanol involves the breakage of oxygen-hydrogen bond, then the alkanol is behaving as who? An acid. Take note of that. But if the breakage involves carbon-oxygen bond, the alkanol is behaving as a base. I hope somebody follows me. Now, in general, let us try to generalize it for clarity purpose and avoidance of doubt. If I write an alkanol, alkanol is ROH, and I react this with a metal M, I'm going to produce ROM. See now, ROM. That means that the bond between oxygen and hydrogen has broken. So hydrogen is given out. Are you with me, somebody? Now, when this happens, this M here is who? That's a metal. Who is this person? Alkanol. Alkanol. Abi, the general formula is ROH. Now, the person you're producing here, which is ROM, an alkyl group, oxo group, and the metal, that's what you call alkoxide. It belongs to the family or the general formula of alkoxides, and this is hydrogen. My people, when an alkanol reacts with a metal, you produce an organic compound belonging to class we call alkoxide, and hydrogen is given out. Anytime this happens, know that this alkanol here is behaving as an acid. Reason. You know what we did in inorganic chemistry? One of the properties of metals is their ability to displace hydrogen from acids. One of the properties of metals is that they have this ability to remove hydrogen from acids. So anybody that can react with a metal and its hydrogen is lost in the process is an acid. So a typical example is this. Watch me. C2H5OH. That is ethanol. If I react this with sodium, what do you think I'm going to produce? C2H5, which represents an alkyl group. Then sodium will now come there. Hydrogen will be given out. So this person produced here is a member of alkoxide. And precisely we call it sodium. Sodium, see the sodium here. Because there are two carbon atoms. Sodium ethoxide. Sodium ethoxide. Sodium ethoxide. That is what I produce. My people, this is alkanol reacting with a metal. In the process, the hydrogen of the alkanol has been displaced by a metal. That means that this person here is behaving as an acid. It takes an acid to react with a metal and lose its hydrogen in the process. Because one of the properties of metals is that they have the ability to remove hydrogen from acids. Remember that in this reaction, it involves the breakage of oxygen-hydrogen bond. That's why hydrogen was given out in the process. Okay, follow me. Now let's take a look at another reaction where the same alkanol is now behaving as a base. Class, watch this. If I have RCOOR, which is a carboxylic acid, and I react this with ROH, which is an alkanol. RCOOH, that's carboxylic acid. And I'm reacting this with ROH. Let's differentiate the R so you don't get confused. This R is the R in the acid. This carboxylic acid. This is an acid, of course you know. And this is ROH, which is an alkanol. Now I'm going to produce RCOOR. What did I produce? RCOOR, which means that this hydrogen here is no longer there. I have RCOO. See, RCOO. Instead of writing hydrogen, I put R. This should be R prime. So this R prime you see here has replaced the hydrogen here. So the hydrogen here has gone out to combine with OH, which is now water. Which is now who somebody? Water. Let's analyze this again. RCOO. The hydrogen was given out. Now, from the alkanol, you have the alkyl group, R prime. Are you with me? So, which bond broke here? The bond between the alkyl group and oxygen, which is carbon and oxygen bond, broke to remove OH. That OH combined with the hydrogen coming from this person to form water. Are you with me? So, the reaction of alkanol here involves the breakage of carbon and what? Oxygen bond. Does that make sense? And in the process, what did we produce? This is ester, general formula of ester. This is an ester now, isn't it? And ester is a salt. And this is water. Class, remember, there's what we call neutralization reaction. That is a reaction between an acid and a base to form salt and water only. So if I produce salt and water here, and this is an acid, then this person must be a base. This person must be a base. It takes a base to react with an acid to form salt and water only. That is neutralization reaction. A reaction involving an acid and a base to form salt and water only. So whenever an acid reacts with an alkanol and you're producing ester, which is salt and water, it means that the alkanol is functioning as a base. In fact, by the time we go deep in this course, you see that this reaction is a reversible reaction taking place in the presence of a mineral acid, and we call it esterification. Esterification. We are coming to that. Esterification. So we can give a typical example of what is happening here. Follow me, class. I can have CH3COOH, ethanoic acid, plus C2H5OH, which is ethanol. What am I going to produce? CH3COO C2H5, which is ester, plus what? Water. My people, I told you this is a reversible reaction taking place in the presence of a mineral acid. So this is an acid. It is reacting with a base to form salt and water. Does that make sense? So in this reaction, this alkanol is functioning as a base. The one we wrote before, the alkanol was functioning as an acid, meaning that an alkanol can behave as an acid as well as a base. That is why we say that alkanol is amphoteric. Alkanol is what, somebody? Amphoteric. You need to be part of this program. Physical classes will start on Monday. Online classes are already on. I don't know what is keeping you. Resist that temptation. Against all odds, be part of this program. My name is Bookish, and you'll be happy. I'm here to breastfeed you, nurture you into academic diamond. God bless you.